Okay, now the candidates, please go ahead for presentation.
Okay. Good afternoon. Today I'm defending my PhD thesis entitled Degradation Modeling and Remaining Useful Life Estimation from Statistical Signal Processing to Deep Learning Models under the supervision of Dr. Amir Asif and Dr. Arash Mohammadi. In this presentation, I'll start with a brief introduction and then move to the first dimension of my thesis, which is the degradation modeling, and the motivation, the main contributions, and some details about the proposed approaches, and ending with the results. And at the end of the first dimension, and then we will move to the second dimension of my thesis, which is the RUL estimation, the motivations, the main contributions, give a brief description about the data set, use the data set, and the common settings and the common techniques used in most of the approaches, and then give some details about the proposed approaches and the results, and ending with the future work. This thesis belongs to the field of the prognostic health management. So what is the prognostic health management? Prognostic health management is a key enabling technology in several industrial and manufacturing applications to provide an early warning of impending failures and to determine the remaining useful life of machinery. Basically, the focus of the PHM is centered around two interrelated search directions: the degradation process modeling and the remaining useful life estimation. From that, we establish our two dimensions in this thesis, which are proposing a general degradation modeling framework and proposing an accurate framework for RUL estimation. That will take us to the first dimension of my thesis, which is the degradation modeling. So what is degradation modeling? Modeling is a key task of the diagnosis process, as it will provide essential information about the health status of the system. And the degradation modeling existing work can be classified mainly in two categories: either stochastic process models or general path models. However, there are some other models, such as the data-driven, that cannot be classified in any one of them. The focus of the degradation modeling of our thesis is about the stochastic process models. And the stochastic process models available in the literature, either based on single stochastic degradation or simplified combination of similar stochastic distributions. And that will take us to the motivations behind this part, where most of these works deal with one specific degradation path, multiple degradation paths, but from the same type. And the second issue is that the model are built, most of the models are built based on a prior knowledge of the true degradation model of the system, which is not the case in the practice. The main contributions of this part are proposing two approaches. The first one is the multiple model degradation path framework, and the second one is the interactive multiple model particle filter framework. Also introducing a new category for degradation modeling that covers a wide range of degradation scenarios. The proposed framework provides precise results without having any prior knowledge of the true degradation model of the system and able to handle different linear and linear degradation models. The proposed degradation models approach, the first one, as we just mentioned, is the multiple model degradation path estimation framework that combines the multiple model adaptive estimation with degradation analysis based on particle filters to derive a set of candidate degradation models. Each degradation model is used to perform state analysis of the system. In this approach, we consider the state space model as based on the equations 1 to 3, where x sub k is the state vector, that is function of the degradation variable, which is already function of the performance vector, variable, and z sub k is the observation vector. The candidate degradation paths in this approach are the winner process or based on winner process and gamma processes, and the degradation state space models as in equations 4 to 7. So the main steps of this approach start with that each matched particle filter developed based on the following optimal Bayesian filtering recursion: basically the prediction and the updating. And then we need to compute and update the corresponding weights of each mode matched filter. Basically, the main target of this step is finding the conditional probability density function, which is this guy, corresponding to a specific mode, degradation path, giving all the observation up to the current time. And after updating and gating the weight, now we can update the global state estimate and its corresponding covariance matrix from the available mode matched state estimates that we already got it from each particle filter based on equation 12. The second proposed model is the interactive multiple model particle filter. And what makes this one different from the previous one is at the beginning of each cycle, the initial estimate is a mixture of all recent estimates from a specific model. This mixing allows the interactive multiple model to take full account of the history of the modes, leading to faster and more reliable estimation for the change system states. And in this approach, we consider the same state space model as before, which is this one. Sorry. And the candidate degradation paths are the same, which are the winner process and the gamma, in addition to the inverse Gaussian. Each degradation matched particle filter is developed based on the Bayesian equations, which are these, equation 8 and 9. And after combining the three model state estimates, we have the associated estimates that we can use to start with the mixing, to finding the mixing probability that based on the transition probability from one mode to the other one, which is this guy, P sub ij. Using this one, we can get the initial state vector and the associated covariance matrix for a specific mode based on this equation, that we will use it to generate MP particles and its normalized weights to to get the state estimate of each mode based on equation 14. Then we will update the weight by taking into the account the Markov transition probability from one mode to the other one, and gave the adaptive weight of each matched filter. As the adaptive weight of each mode matched filter is found, then we can combine the local state estimate and form the global state estimate based on equation 16. For the simulation results, for both of them, for both proposed models, we consider the commonly used three-vessel water tank system that developed by a German company called Amir Automation. In figure 3A, we can see that the adaptive weight belong to the associated with the Brownian is converged to 1, as it is the active one, while the other one, which is gamma, evolves to 0. The same here for the RMSE, where the proposed model and the Brownian, which is the true path here, evolves to 0, the error evolves to 0, converges to 0, while the other one, which is not the true one, the gamma one, continue to increase. For the second approach, we can see we have three degradation paths. And in the first figure, we can see that the active one here is, or the true path here is the Brownian one. So that's why the probability here is 1, while the others are 0. And here, when the gamma is the true one, then the probability is 1, while the others are 0. And for the root mean square error, we can see that each standalone model goes to infinity, continue to increase, while the proposed model is bounded. That's the end of the first dimension of my thesis. The second dimension is based on the RUL estimation. So what is RUL? The RUL is the residual lifetime during which a device can perform its intended function. In other words, the device can work properly without any repair or replacement. The leading industrial and manufacturing companies try to use the advancement in predictive analytics and machine learning to come up with the new data science methodologies and sophisticated algorithm, basically to move from showing what happened, which is the traditional way of maintenance, to predicting what will happen in the future, which is the new phase of prognostic health management, the predictive maintenance. So the main objective of RUL estimation is to provide an early warning of any failure. To classify the existing work for RUL estimation or RUL estimation in the literature, we can classify them in two categories or two classes. Either the standalone, which is represented by either only physics-based or only data-driven, or hybrid class that based on multiple physics-based or physics-based and data-driven, mixed between them, or multiple data-driven. And the focus of our thesis is basically for the multiple data-driven, specifically the multiple deep neural network techniques. And that will take us to the motivation, where the hybrid has the ability to overcome the weaknesses and the limitations of individual approaches, in addition to taking the advantage of unique features and benefits of different approaches. Excuse me. And not to forget the exceptional success and the diversity of the different deep neural network techniques. The main contributions for this part were proposing the first parallel hybrid deep neural network models in the literature, in addition to proposing the first noisy hybrid deep neural network models in the literature, also proposing the first noisy multipath hybrid deep neural network models in the literature, all of them for RUL estimation, definitely. Utilizing Monte Carlo simulation to evaluate the effectiveness and robustness. And basically, it's rare to find the Monte Carlo simulation in machine learning or deep learning, sorry. There is only one paper about that. So, and they didn't use it for the testing part. Improving the result between 20.7 up to 64 and 12.7 up to 21 in terms of the score and the RMSE values, but we will explain them later. The models have achieved these outstanding outcomes with only 42,000 up to 77,000 parameters, utilizing and investigating different styles and values of noisy training and evaluating their effects on the proposed models. And finally, employing the batch optimization technique with bidirectional GRU to improve the RUL estimation. Before going with some details about the proposed models, we need to give a brief description about the used dataset. The proposed models are implemented and evaluated by using the CMAPS dataset provided by NASA. The CMAPS is a simulation software that simulated several scenarios of the degradation behavior and the fault impacts of the main components of a big commercial engine, turbofan engine. And these components are the fan, the low pressure compressor, high pressure compressor, low pressure turbine, and high pressure turbine. As you can see in the table, the data set is divided into 4 sub-data sets ranging from FD001 up to FD004. Each settings has different train trajectories and test trajectories, and they are simulated based on different operating conditions and different fault modes. These data based on reading of 21 sensors. However, only group of 14 sensors were selected. The minimax normalization has been used to ensure equal involvement from the readings of each sensor. To evaluation the proposed models, we use two matrices. The scoring function, which is an evaluation measure that proposed by PHM Society in 2008, and it favors the early predictions more than the late predictions. And the most popular measure for evaluation the performance, which is the root mean square error, that assigns equal weights for both the early and late predictions. We use common settings and common techniques in most of these proposed approaches. We consider the RUL a prediction for system or subsystem with n machinery units, such as the turbofan engines in our case, based on run to failure sensor measurements. We use L sensors for monitoring each unit. The collected sensory data will take the following matrix form: X sub n, where X to T is the observation vector. We used different techniques, such as the sliding window technique, to prepare the samples for better feature extraction, or the piecewise linear degradation for labeling the data during the training stage, and the early stopping and the dropout for avoiding the overfitting problems. In addition to the backpropagation and mini-batch gradient descent techniques for the training, and the adaptive moment estimation technique for the optimization, mean squared error has been adapted as the loss function, and we use the grid search technique with different strategies to optimize the trainable parameters. When it comes to the RUL proposed approaches, in our thesis, I can categorize, I can classify the proposed models in three groups. The first group is the hybrid deep neural network models, I call it G1. And the second group is the noisy hybrid deep neural networks models, G2, and the multipath parallel hybrid deep neural networks models, sorry, G3, it's by mistake. Excuse me. The first group, which is the proposed hybrid deep neural networks models, the parallel hybrid design with multiple types of deep neural networks will enable the model to collect more informative features, as each deep neural network technique has the ability to capture a specific pattern from the input data, resulting in different features and advantages that will aggregate to form the desired output and enhance the predictive efficiency. We can see from in all the proposed models, based on two parallel paths, followed by a fusion center that will combine the result of the two parallel paths to form the RUL. The second parallel path, the second parallel path and the fusion center have a common design among all the proposed models, where the second parallel path is based on the convolutional neural network, 3 layers of that, and the fusion path is based on 3 fully connected layers. While the first parallel path use different deep neural network techniques, starting from the LSTM to the bidirectional LSTM, the gated recurrent unit, and the bidirectional GRU. In this part, we can see that the main component, the main components of each parallel path. So we can see that we have used different settings with different values. While the second parallel path, as I said, has a common design among all the proposed models, which is based on 3 CNN layers and 2 max pooling layers. The third path, which is the fusion path, that used to combine the result from the two parallel paths. It's a common design, but based on three different settings, as you can see. So the main results of those proposed models based on this box, the first four proposed models. We can see in this table that we achieve the base result in terms of the FD002 and FD004, which are the most complex scenarios. And the achievement was between 13.5 up to 44 in terms of the score function, and around 6.5 in FD002, and around 4.2 in terms of the RMSE. However, the other models, most of them, I mean, the models that they're competitive to us, all of them just proposed after the publication of the first parallel model, which is the HDNM. The second group of the proposed models, which is the proposed noisy hybrid deep neural networks. In this part, the main target was to improve the robustness and the generalization of the behavior of the first proposed group of models. And to do that, we need to enhance or improve the learning capability and increase the learning capability. And we can do that by improving the training stage. And in the literature, there is a long list of proposed models to training stage. Among this long list, adapting noise training or adding random noise is an effective approach to increase the robustness and reduce the generalization error. And why is that? Because this property or this technique has the data augmentation effect, and it has the ability to reduce the generalization error as well as avoid the overfitting problems. We achieved that in our proposed models by injecting Gaussian noise layer, which is an effective technique. You can see in all the models, we have one standalone Gaussian noise layer in each path. And for the first two proposed models, we use the Gaussian noise layer, injected that Gaussian noise layer in only two parallel paths. We called this style partial noisy training. While the second two approaches, we adopted something we call it fully noisy training, as the injected noise layer in all the paths of the model, in addition to hidden noise layer in the first parallel path. And there is something important here to be highlighted, that the noise injection technique during the training stage is a generic strategy that can be used regardless of the type of the problem being tackled, and no matter what type of neural network is utilized. The main components of the proposed models, we can see it's exactly the same settings as in the previous group, except that we adding the Gaussian noise as we previously mentioned. We used different levels of Gaussian noise here, and the same settings here for the as before, except that the two injected noise layers. And for the fusion path, fusion center, we have two styles, without noise and with noise, with three different settings. In this part, in this group of the proposed models, we studied different effects on the RUL estimation results. So the first effect that we studied is the effects of the operating conditions and fault modes. In these figures, you can see that in the first settings and The third setting, the error periods in both of them is less than the error periods in second and the fourth one. And the reason behind that is that the second and the fourth one have been simulated based on 6 operating conditions, which means that we are dealing with very complex scenarios. While the first and the third one, they are simulated based on 1 operating condition, which is the sea level. We can conclude something here, which is that the number of operating conditions has a larger impact than the fault modes, as the second one and the fourth one sharing the same number of operating conditions. The second effect that we studied here, we studied the effect of the noise level, where we chose 2 models from the proposed models, which is the noisy bidirectional LSTM and the noisy parallel bidirectional GRU. And we use a level of 10 times the usual level of the noise. And we can see that the model is still able to capture the mapping from input to output, and the result also outstanding. Something to be highlighted here, that we can see the noisy parallel bidirectional GRU model, it has the effect of the noise on it has higher level than the other one. And the reason behind that the noisy by LSTM follows or has the partial noisy training, while the other one has a fully noisy training. And here we studied the effect of adapting the noisy training, basically to show how much effective following the partial from the fully noisy training. We can see that the first table, the first part, we followed the partial noisy training, while the second one, we followed the fully noisy training. We can see that the improvement levels in the fully noisy training much higher than the partial. However, the fully noisy training is very sensitive to the noise level, as we saw before. So to compare our result to the state-of-the-art methodologies available in the literature, we can see that we achieved the best results ever in the literature up to date, especially the noisy bidirectional, the noisy parallel bidirectional GRU, which is based on the fully noisy training. The third proposed group, which is the proposed multipath parallel hybrid deep neural network model, in this part of the thesis, we went beyond the traditional structure of the hybrid model, which is with 2 parallel paths, and developed integrated multipath parallel hybrid framework based on 3 parallel paths. Basically, the design of these models stemmed from a profound concept, which is the more informative features that you collect, the better the result you will achieve. And we know that the effectiveness of all machine learning algorithm literally depends on how you present the data. And we know that the extracted features represent the characteristics of unobserved phenomena and characterize the underlying problem from the available data. That's why, or hence, the purpose of extracting more feature is to provide more knowledge about the data that will lead to enhance the learning process, and as a result, to achieve better results. All the proposed models have been designed based on 3 parallel paths, followed by 1 fusion center path. Here we employ different styles of noisy training and different deep learning techniques, and even different design for the usually the the common parallel by CNN. Here we use different styles, different techniques, such as the global average pooling, where you can see that we use it in almost three proposed models. And also we we use the batch normalization successfully as a standalone layer in the last proposed model, which is the DDHA, between the bidirectional GRU layer and the first GRU layer, to normalize the normalize the data and to stabilize the learning process. We can see that we have different settings for the parallel paths, and we have different styles, different techniques, and different settings for the third path. And for the fusion path, we have a common design among all the proposed models, which is based on a 3 fully connected layer and 1 hidden to hidden injected noise layer. And we can see we have 3 different settings, all of them based on the rectified linear unit activation function. And the results, we can see in the first figure, which is figure 16, that the predicted RUL values closely follow the ground truth, especially when the RUL is small and the prognostic accuracy is highly needed. The same in the second figure, when we selected randomly 4 different units, tested the prognostic on them, we can see that the accuracy or the result, they are in line as in the previous results. We studied here the effects of multiple parallel paths on the RUL estimation results to show how the multiple paths of the 3 paths are effective as compared with the 2 parallel paths. So we selected 2 models. In each model, you can see in the first model, we compare the proposed model with 2 combinations. The first combination by removing the first parallel path and keep the next 2. And the second combination, or the second design, by removing the second path and keep the others. Sorry. So we can see that the using or adopting the 3 multiple paths has improved the results remarkably. So we can see the difference between the results. However, the rest are also good results. But adding the third parallel path has improved the results remarkably. And basically, the general speaking, why is that? Because the main target, as I said before, to ensure the best investment of all the used deep learning techniques in terms of extracting as much informative, relevant and non-redundant features, as we are using different deep neural networks in parallel. The second study, we studied the effect of different time window size. So we used time window size 30 and 15. The main idea of that to show how the model is stable and how the effectiveness of the model, where we know that whenever that the size of the time window is longer, then we have more information. So most of the proposed approaches in the literature, they use 30. So what I did here, I used 15, which is 50% of the 30, and still my results are better than most of the reported results in the literature. Here we studied the effect of the noisy training on all the models. We can see that adapting the noisy training in each one has improved the results for all the proposed models. We studied the performance evaluation with additive noise. So For the first time, we are using here the Monte Carlo simulation to add noise during the testing stage. The main idea of that to show how the model is robust to the against the noise. So we use different levels of signal to noise ratio, and we can see that our results still outstanding even with this level of noise, and that to prove the robustness of the proposed model against the noise. Here we can prove also how the model is stable and what makes the model more effective and powerful when we added the third parallel path. So we compared the result after the additive noise, I mean during the testing stage, between the two parallel paths, the previous group, and the multi-path parallel paths. And we can see that the improvement is really high and big. Why is that? Because adding or adopting multipath or adding the third parallel path is it has a role in reducing the generalization error and improving the robustness. The achieved result of all the proposed RUL estimation models, starting from the first proposed model up to the last model proposed in this thesis, we can see the improvement in the score value between 27 to 38% and between 9 up to 23% in terms of the RMSE. When it comes to compare the our proposed models, especially the last proposed group, which is multipath, to whatever available in the literature, we can see here these are the base results reported up to date. We can see that we achieved the base results up to date. So, and the improvement were 20.1, around 20.1 up to 64 in terms of the score values, and between 12.7 up to 21 in terms of the RMSE. Even with the models that they didn't follow or use the piecewise linear degradation, our models achieve the best results. The main contribution of this thesis is basically introducing a new category for degradation modeling that covers wide range of degradation scenarios by proposing two models, the MMDP and the IMMPF, and proposing for the first time the hybrid deep neural network model, the noisy hybrid deep neural network model, and the multipath hybrid, noisy multipath hybrid deep neural network models for RUL estimation for the first time in the literature. Utilizing Monte Carlo simulation to evaluate the effectiveness and robustness during the testing stage, employing the batch normalization technique with bidirectional GRU to improve the RUL estimation, and achieve the best reported result in the literature with only 42,000 parameters. For the future research, one can consider the exploration of the deep learning techniques such as capsule network, or utilizing other ways than the piecewise degradation model for labeling the training data, or incorporate uncertainty quantification for the future, and in addition to considering and investigating how feature can be extracted more efficiently to further boost prediction accuracy. These are the list of my publications. And that's the end of my presentation. Thank you so much for listening.